All right, so let's get started with the episode number 3 with deep learning, machine learning. In this example, we are going to see a classification example. So let me just open my notebook so I can start explaining you. So before going to the next lecture, let me just review what we did last time. So last lecture, if I want to show you what we did last time. So we basically try to create a neural network, a single neuron. Basically, whenever you give an X, it predicts a Y. So that was nothing but a regression example. So we try to develop the equations for that. I told you the neural network has two parts, that is the forward propagation and the backward propagation. We developed the equation. So basically we had one inputs and one output. This is the equation for the error. Then we have the sum. Then we calculated the gradient. So basically it's nothing but the chain of partial derivatives. So we learned how to calculate gradients. Then we developed the equations for the updated weights and biases. So far we have not we are just trying to learn the mathematical part right now, and then we will jump into the coding itself. I did show you a code last time, but I would rather focus right now on the mathematical equation, and slowly, as we get gradually have a good idea about deep learning, we will do coding as well. I would from the next lecture I would also include the delta rule. So without wasting much of time, let me start with the classification example on a deep neural network. So let me just choose a paper so that we can start quickly. All right, so we are ready. Let me just choose a color. Now we are solving the classic example for classification. So let me just draw a graph. All right, I have a task. Basically, my company has said me that let's say this is 0 and 1, 2. So if I would be supplying 2 points x and y based if it is above the point, if it is above the line, it should be O category or 0 category. If it is below the line, it should be X category. On if any points are on the line, that should be basically just 0. So my job or my bosses have asked me to design a neural network which will classify basically if I give in a points x and y, it will tell me whether it's an O category or an X category, or whether it's a 0 or 1. That's a classification, a classic binary classification. So let us draw the neural network and let us draw the neural network and do the mathematical part first, and then we'll jump into the programming itself. All right, so I have my neuron here. I'm gonna change the color to yellow so that everyone can follow here. All right, so I hope this is visible. So as you know, the neural network has two parts, that is the summation unit and the activation units. Now, excuse me, we have two inputs. So basically the user would provide 2 points, and based on that we need to classify whether it's a O or X category. So x1, x2, and as you know, every neural network has something known as bias. And don't forget to write the notations. This is a, S is a, and of course after this it has to pass through a loss function. So we are going to calculate the loss, and then we propagate backwards. So let's write the equation. So what is the equation of x? W1 x1 1 times b. Do you guys agree? Yes, right? This is the equation for x, right? Let me just make sure my video is recording, otherwise, yep, that's fine. So just want to make sure it's recording. All right, so we have the equation for S. Then we need the equation for A. So what is A? Basically it's nothing but a rectified linear unit right now. So simple x, right? So I'm gonna say or else let me introduce you to the first activation unit, that is a sigmoid. Actually, you know what, let me just go with the rectified linear unit, that is simply x, because it would be confusing right now if I introduce softmax and stuff, because the equations and all would be confusing. So let's just go ahead with the basics. Okay, so S is equal to w1 x1 plus w2 x2 plus 1 times b1. A equals to S. I'm simply passing S. All right, now I need to calculate the error, which is given by the formula. All right, do you guys agree? So far good. All right, so moving forward, now I have done my forward propagation. So this is nothing but the forward propagation, right? So let me cut this part and paste it a little bit down. Now I need to propagate backwards, right? I have the equations. Now I need to compute the gradients, the deltas, and stuff like that. So for the first of all, the first equation would be I need to calculate W1, W2, and B, the gradients for all these three, because I have to update all of these equations. So how do I do that? So it's pretty simple as usual. So let me show you the path. Now I want to go, let me take a red color so you can see that. Now I want to compute W1. So the path would be this way, right? So could you write the equations for that? Let me make the window a little small. So if I say, so this, pretend this to be the loss L. So this is gonna be dl with respect to dA with respect to ds with respect to dw1. Do you guys agree? Simple, right? I'm just writing the chain rule. That's what I showed you. Now I need to write for the equation. Now I need to write for this W2, right? So this will be this way. Do you agree? The path, right? So let's write the equation. Del L by del A, del A by del S by del W 2. Now I need to write for the equations for the biases. Del L by del S by del A. Oh, sorry, my mistake. Del L by del A by del S by del B. All right, now let's compute the gradients for each of them. So we have L with respect to A. So L is nothing but my E, right? So what is the derivative of this function, guys? We did it last time, right? So this is gonna be dl by dA, or I can say dE with dA half y minus a into 2, oops, sorry, not into 2, into minus 1, because derivative of a is minus 1. So this will be minus of y minus a. Do you guys agree? Yes, so far good. Great. So moving forward, now what is the derivative of a with respect to s? This is nothing but our linear function. The derivative of this has to be 1. So this one, so derivative of this is 1, right? So oops, let me zoom out. So this has to be 1. Do you guys agree? Now s with respect to w1. Now let me take a different color. If I differentiate this with respect to w1, so I'll get x1, right? So this has to be x1. Now without even calculating, can you tell me the equations for w2? Simple, right? What is this? Same as this, minus y minus a. What is this? 1. What is this? x2. Simple, right? So you can do the math. It's gonna come out the same. You can just do it on a piece of a paper. It's pretty simple. So L with respect to A, again minus y minus a. It's the same thing. We have the same thing. A with respect to S is 1. S with respect to B is 1. How? Let me show you now. Otherwise people will say, hey, what's going on? So S with respect to B. So here derivative of B is 1. Rest everything is 0. So it has to be 1. So if I write the final equations a little neater way, of course, yeah. So dE with respect to dw1 would be minus of y minus a into the derivative of the activation function, which is 1, into x1 into x2 So these are my 3 equations. Now I know it's a little bit messy here, so let me just go through my notes so I can show it to you what we did so far. Alright, this is a little neater version. So that's what I did. Basically these are all the equations. So if I want to write the equations once again on a paper, so dE with respect to dw1 was what, guys? Minus y minus a into derivative of activation function into of course the input, so y minus a into 1 into x2 minus y minus a into 1 into 1. So these are my equations that I need to code in my software. All right, then I need to update the weight. W1 equals to W1 minus alpha is nothing but the learning rate into dE by dW1. So this value comes here. Similarly for W2, and B equals to B minus alpha times, oops, so B equals to B minus alpha times, that is nothing but learning rate times the gradient of with respect to bias. So that's the mathematics basically. Now let's move to the software itself. Let's learn how to code it. So let me just open my notes and show you. And before that, I need you guys to get started with the delta rule. So I'm gonna cover the delta rule next time. So for now, we know the equations. We already did the equations simply. So dE with respect to dW1 is delta 1, which is nothing but minus y minus a into 1 into x1, which is nothing but the same thing that I wrote. So let's see the software part now. Wait, I'm just trying to erase this. All right, now moving to the coding. All right, so let me see if I have my IntelliJ. Yep, that's right. Now yep, that's the entire code. So I have two inputs, so x1 and x2 I declare is as training inputs. Then training inputs dot shape, so I define the shape. So basically this is 2 rows and 4 columns, so I'm just trying to get the shape. Number of epochs equals to 1000, so I'm defining the number of epochs. Then training output is equal to output, so basically for my inputs, that is 1 2.2, classify this as a O category or 0. For 1 2.4 it's a 1 category. So I'm giving my inputs and outputs. Basically this is a supervised learning because I have labels that will be covered later on. So number of neuron equals to 1 because I'm using 1 neuron. Now this is the coding starts. Now here comes the coding. np.random.seed equals to 1. Basically I want to initialize the weight randomly, so the size of the weight matrix would be training inputs shape comma number of neurons. I know so basically what is my weight matrix size? Okay, let me move to my this one. How many weight matrix do I have? 2, right? Okay, now let's go to the code. Weight matrix equals to the random.random training inputs. So how many inputs do I have? So if you see the number of inputs dot shape 1, so that is nothing but 1 comma number of neuron is 1. So training inputs dot shape, so basically this will be 2 because I have 2 inputs, that is x1 and x2. So the weight matrix will be 2 comma 1 because I have 2 weights. If I see my code, how many weights I have? 1 and 2. So I have 2 weights. So basically the shape of the weight matrix will be 2 comma 1. Remember, the shape of the weight matrix is the output neuron with respect to the inputs or the input side. Similarly, the bias matrix, I define it as np.random.random number of neurons comma 1. So basically that is the shape of the bias matrix. So I am defining the forward propagation. So for training inputs, so basically I'm defining the number of epochs here. So for the number of epochs here you can see, then I'm defining my data. So I get the first set of data, then I do the forward pass. Basically sum equals to np dot, so you can see wx plus b. That's what we did, right? So if you observe, what was our sum? Our sum here was wx plus b, right? So that's what I did. Let me just, yeah. So if I want to show you this a little, if I can zoom this a little bit, sum equals to np dot training inputs dot index weight matrix, that is xw plus b. That's what I'm doing. I am just coding what I wrote I'm just coding the math now. Then actual output equals to 1 upon 1 plus np dot. This is basically a sigmoid function. You can type this as, I'm sorry, AC actual output equals to sum. So in our case we were using just the linear function. So that would be this. Otherwise, if you're using a sigmoid, that would be this. We would be covering that on the later part, that is sigmoid, the softmax, everything in the later part, because that's a little bit complicated right now. Now I'm calculating the error equals to half y minus a the whole square. So you can see y minus a. So that is y minus a. So let me show you the equations of error. So here you see the equations of error. That is half y minus a the whole square. Error half y minus a into y minus a. Just coding the math. Then I need to calculate the derivative of the activation function. So the derivative of the activation function here was 1, because we were doing a simple linear activation function. So that's going to be 1. So here you are going to say 1, not this. So you can change that. And simply I'm just writing the gradient w, which is nothing but delta, which is nothing but derivative into activation function. So if you see derivative error, that is minus of y minus a. So minus of y minus a into the derivative of the activation function, which would be 1. So that is nothing but our gradient. So let me move over the equation. So see this, this is nothing but delta times x1. So what is my delta? Nothing but this. I'm gonna cover the delta rule in the next video. So so basically we just develop the math, right? Let me just write it here. Into 1 into, so this is what I need to code. So if you move the code, so we have delta, which is nothing but minus y minus a into derivative of the activation function into the inputs. So here you have the inputs, because in the equations we have input x1, you see. So we have the inputs, and similarly grad b is equal to delta, that is nothing but minus of y minus a. Let me erase that. Delta, which is nothing but minus of y minus a. We just did that, I don't need to explain you once again, and that's what it is doing. Now let me run this code and show you the simple classification example. The code will be there in the description section. Please feel free to download it, play around with it. So now it's it's the learning is done. Now it is asking me for inputs. So if I supply 2 and 2.7, it should give me 1. So let's see, 2, 2.7. Neural network predicted. So my neural network says 50%. So it says it's 50% class 0 or 50% class 1. So it's not accurate right now. So as I said, you need to train it more for more number of epochs. So we can do that later on in the later videos. So this is just for your explanation, what is the math, how you code the math. Now I want to derive something. I want to tell you something about the delta rule, so which will basically be very efficient while we are coding the big programs, basically the MNIST data set. So if you see, I use a delta rule a lot in these kind of codes. So let me show you, or let me explain you the delta rule now. Let me move towards my notebook once again. So what is delta? Basically delta is nothing but, let me erase this. Remember guys, so let me just take a new page. So if I draw a new neuron here, have the activation function, I have one input x1, x2, I have bias. Okay, this is s a, whatever we did, right? Loss. So we said what was del e by del w1, which was nothing but I said del e by del e by del a by del s, and del s by del w1, right? Now remember, delta is nothing but this part. I say this as delta because this is repeated in each and every gradient while calculating that. So while coding it, this will be a very efficient thing. So what I would say is, what was this? Minus y minus a. What was this? A with respect to s, derivative of the activation function. So that's my delta. So I say delta is nothing but this. So my gradient becomes delta times, that is nothing but s with respect to w1, so x1. So I write the code for delta, and I simply do it for each and every neuron. Now let me move over to my notes and see if this makes sense. So error equals to y minus a the whole square. Delta 1 equals to minus y minus a1 into 1. If you're not sure, so how did I calculate that? So remember, del E with respect to del W1 would be del L by del A. So this is a del A with respect to del S and del S with respect to del W1. This part is my delta, or you can say delta is derivative of error into derivative of activation function. This is the thing, my delta. Remember this very carefully, it's very important. What is my delta? Please speak it loud. What is delta? Delta is nothing but derivative of error into derivative of the activation function. So let's see, derivative of error, does this make sense? Yes, it is. That is the derivative of error. That is, if I take a derivative of this, I get this. So that makes sense. Into the activation function, derivative of the activation function. So is this the derivative of the activation function, guys? Yes, it is. So that's what my delta is, you know. So if I move to the code now, and I think this will make sense now. So I calculate the sum, that is wx plus b. Then I calculate the actual output, that is nothing but a sigmoid right now. Then I calculate the error. Now see this, I'm calculating delta. What is delta? As I said, derivative of error into derivative of activation function. So I have defined both of them up. So I have my delta. Now what is gradient? Simply delta times training inputs. So it's that easy. So while programming, it's easy. So that's why we use delta rule. So what is grad b? Simply delta. Now let me show you how grad b is delta, or let me explain you rather. So what is basically grad? Let me move it, sidetrack you here. So what is del E with respect to del B, which is nothing but del E with respect to del A with respect to del, come on guys, what it is? So S, right? S with respect to B1. This is my delta. What is delta? I said derivative of error into activation function minus y minus a into 1. That's my delta, which is here, into derivative S with respect to B. So what is my equation? So if I differentiate this with respect to B, this is 0 and this will be 1. So I get 1, right? So what is this? Basically simply delta. It's just delta, right? This is just math. Basically just sit with a piece of paper, try to practice the equations what I said. If you understand the concepts here, what I'm trying to say, everything rest would be a cup of cake. You if you feel bored, oh, this is pretty easy, why am I stressing so much here? Because if you know the delta rule, you can add multiple hidden layers, which we are going to learn. Then we are going to do a lot of optimization. So you can see everywhere we have delta rules. So that's why I'm focusing a lot right now on delta rule. And because once you know the delta rule, we need to program this in the Python. So we are also going to do that. So that's why first understand the basic, understand the mathematics, and once you have a good idea of the mathematics, you can go ahead and program in Python. So few more videos would be mathematical videos, then we would be jumping into programming, because right now if I jump into coding, and you would be scratching your heads and saying what's going on, I don't understand anything, and you will just stop learning deep learning, which I don't want exactly. So I want you guys to learn the basic, to learn the mathematics. If anyone wants my notes, you can email me. I'll definitely try to email you all my notes. So email me at shahsoumil519@gmail.com, and I shall email you my notes. And for now, we are at the classification. I have already introduced you to the delta rule. What is delta? Again and again I'm saying, once again, why? Delta is nothing but derivative of the error function into derivative of the activation function. Keep this in mind, very important. Now the shortcut or the trick is, what is the, if you want to write directly, what is gradient of W1? So simply delta into the output of the previous layer. Okay, so what is the output of the previous layer? Here is x1. Similarly for W2, it's x2. So that's how you remember it. So if you want to calculate it quickly, so once you practice this a lot, you would gradually be very confident on writing equations, and once you know the equations properly, you can code this in Python. So I hope you guys like my videos. This is episode number 3, I suppose, and I would see you in the episode number 4, where we would be adding 2 neurons instead of 1 neuron, and we would be writing the equations, the math, and we would be trying to program on Python. So that's it for this video. I hope you guys enjoyed it, and if so, do give a like, subscribe to my channel. If you have any questions, suggestions, please leave them in the comment section below, and if I did any mistake, please let me know by doing that in the comment section below. Thank you very much, and I shall see you guys in the next video.